Yeah. Hello and welcome to this course on cosmology. So this is the second part of the course where we will be discussing the thermal history of the universe. In the first part, we have already seen the cosmological dynamics. So we have seen that how the dynamics of the universe works. What we have done, let me quickly recapitulate. So we have solved the Einstein's equation. Okay. So this is the Einstein equation, and we have taken the solution of the Einstein equation as the FLRW metric. Okay. The reason for taking FLRW metric as the solution of the Einstein equation was that it is allowing an expanding universe. Okay. It allows a homogeneous and isotropic universe. Okay. I mean homogeneous and isotropic in space, not in time. Okay. So when we solve the Einstein's equation with FLRW metric, we get a set of three equations. Okay. These three equations are nothing but the Friedman equations. And these three equations generally govern the dynamics of the universe. Okay. And from these three equations, what we have understood is that the dynamics of the universe generally depends on two important things. The first is the type of matter which is there in the universe, and the other is that what is the curvature of the universe. Okay. So depending on what kind of matter is there in the universe and depending on what is the curvature of the universe, the dynamics of the universe will change. Okay, different type of matter can be of, okay, it can be radiation, it can be dust, it can be dark matter, it can be dark energy also. Okay. So depending on what kind of matter is there, okay, each type of matter will have its own equation of state, and depending on that, uh, the dynamics of the universe will change. And the other thing is the curvature. So there can be three kinds of universe: universe with zero curvature, which is known as the flat universe; universe with positive curvature, which is k is equal to +1; and universe with a negative curvature. Okay. So depending on what is the curvature of the universe and depending on what is the type of matter in the universe, the dynamics of the universe will change. Okay. So this is what we have seen in the first part of the theory, where we have solved the Friedman equations for different cases, and we have seen how the universe will eventually uh, go. Now, when we talk about thermal history of the universe, so we will use this knowledge and we will see that what will happen in an expanding universe, okay, with realistic problems. So we will be taking the time scales of the universe. So we will be taking studying the history of the universe from 10 to the power minus 40 seconds to 10 to the power 16 seconds. Okay. So this is the earliest time where our known physics works. Okay. And this is corresponding to the age of the universe today, which is around 13.8 billion years. So from this time to this time, okay, what are the key events which took place in the universe are explained using the thermal history of the universe. This is not a complete theory right now. There are a lot of open questions in this theory. We will be discussing what this theory proposes and what are the things which are known to us and what are the successes and the failures of this theory. Okay, so it is very successful theory and right now one of the best theory to explain the history of the universe. Okay, so the reason for taking the initial time at 10 to the power minus 40 second and not taking t is equal to 0 is because that at time scales below 10 to the power minus 40 second, uh, the classical gravity will not work. You need a quantum description of gravity, and still we don't have any quantum description of gravity right now. So since we don't have it, we can only work with this limit. So 10 to the power minus 40 seconds to 10 to the power 16 seconds. Now, once we before beginning this theory, okay, we will be studying a few important things which we need to understand high energy physics. Because right now, when we understand very early universe, so as you go back in time, okay, as you go forward in time, you see that the universe will expand and expand, which we see every day. But if we go back in time, it means that the universe will every day compress and compress. So if we go to around this time, the universe will be a very tiny thing, okay, and this tiny universe is so tiny that it can be treated quantum mechanically. So, you can see that the universe is the biggest thing today which we know. And at earlier times, even the universe can also be treated as a quantum mechanical particle. So that is the important thing. So from this quantum mechanical particle to this large universe which we see today, which has a lot of galaxies, which has superstructures, stars, heavy elements, light elements, how all these things came into being, okay, is all the part of this theory. Okay. Now, so let us begin with the concept of natural units. So natural units are the most important units when we work with high energy physics. Okay, so when we are working with high energy physics, okay, because right now when we go to very early universe is a very hot and very compressed state which is having very high energy, because as you back in time the temperature of the universe will increase, and as the temperature of the universe increases the energy of the universe also increases. So at very early universes the energy of the universe was very huge. Okay, so in early universe things were of very high energy. So when there is very high energy, okay, the particles with high energy are generally relativistic. Okay, and the things were microscopic. Okay, now whenever the things are relativistic, okay, we use the principle of special theory of relativity, and when the things are microscopic we use the principles of quantum mechanics. Now, whenever there is any expression of special theory of relativity, you will always encounter a constant, which is the speed of light. And whenever you are doing quantum mechanics, you will always encounter constant, which is the Planck's constant or the reduced Planck constant, okay, which is h upon 2 pi. So, so now the problem with these two constants is that this is of the order of 10 to the power 8 meter per second, and this is of the order of 10 to the power minus 34 joule into seconds. So these two constants always come with a very huge, okay, exponent, and this can be of any order. If you are having c square, okay, or h bar square, then these things will unusually dominate and will make the expression very cumbersome, and especially during the calculations, the numerical calculations. So what the plan is? The plan is to make to set them equal to 1. Okay, we have to set the speed of light and the reduced Planck constant to 1. Okay, so this is known as the natural units. Okay, when we do this, we call it as natural unit system. Okay, whereas what we use in everyday life is the SI unit system. Okay, where C and H bar are having their usual numerical values. Okay, so I want to explain you that how this concept of natural unit works. So now every physical quantity, okay, any physical quantity can be written in terms of, okay, three fundamental things, which is the mass, length, and time. Okay, if I write in units, it is kilogram, meter into seconds. Okay, and it will have some exponents. Okay, let me write kilogram raised to alpha, meter raised to beta, and second raised to gamma. So if I want to find out the dimensions of mass, here alpha will be equal to 1, beta will be equal to gamma equal to 0. Okay, so I will be having kilogram. If I want to find the dimensions of velocity, it will be alpha is equal to 0, beta is equal to 1, and gamma equal to minus 1. It will give me meter second inverse. Okay, and similarly you can find the value of alpha, beta, and gamma for different values of physical quantities. So for different physical quantities, the value of alpha, beta, and gamma will change. Okay, but this is a general expression which you can write for any physical quantity. Okay, so we will use this general expression and we will find that how you can relate it with the natural units. Okay. So now let me write here kilogram raised to alpha, okay, meter raised to beta, and second raised to gamma. Okay, and if I write it, okay, I can also write this as, I can replace kilogram with energy by c square. Why I have done this? Because I know E is equal to mc square. Okay, which is, this is the mass, and mass can be written as energy by c square. So this is the mass which can be written as energy by c square raised to alpha. This is length. Okay, E is equal to hc by lambda. If I use, then I will be using h bar c by E raised to beta. And if I write it, okay, E is equal to h nu, then I can write this as h bar upon E raised to gamma. Okay, so this and this both are same expressions. Okay, LHS is equal to RHS. Okay, both are, I have not taken any approximation up till now. Okay, and this can also be written in terms of E raised to alpha minus beta minus gamma, h bar raised to beta plus gamma, and c raised to beta minus 2 alpha. Okay, so this expression and this expression are same. Now, okay, suppose you want to write now, okay, now in natural units, what we will do is, we will take h bar is equal to c is equal to 1. Okay, so what will happen now? I am only left with e to the power minus alpha minus beta minus gamma. Okay, so suppose now if I want to write the dimensions of mass, okay, so for mass we have seen alpha is equal to 1 and beta and gamma are equal to 0. Okay, so alpha is equal to 1 and beta and gamma are equal to 0. So if I write this, then the dimensions of mass will come out to be e to the power 1. Okay, because beta and gamma are equal to 0. So in natural units, mass will have the dimensions of energy. Okay, it is simply like this: E is equal to mc square. Okay, now if I take c is equal to 1, then energy is equivalent to mass. Okay, suppose if I want to write the dimensions of velocity, okay, then for velocities it is alpha is equal to 0 and beta and gamma are equal to, beta is equal to 1 and gamma is equal to minus 1. If I substitute it here, okay, then I will be getting, okay, dimensions of velocity as e to the power 0. Okay, so velocity becomes dimensionless. Okay, So this is the dimension of velocity in the, okay, this thing. Okay. Now suppose if you want to convert from natural units to this SI unit, then just plug in what will be the h to the power beta plus gamma and c to the power beta minus 2 alpha, and this will give you the correction factor. Just multiply that correction factor and you will go back to the SI unit system. So I have the table with me, okay, which is taken from the book of Daniel Bauman, okay, T. Bauman's book, okay, which is Cosmology, okay, published in the year 2021. Okay, so this is the table which is taken from his book. So you can see that the dimensions of mass are is energy, and the correction factor is c to the power minus 2. So you can multiply it and go back to the this thing. The dimension of length is energy inverse. The dimension of time is also energy inverse. The dimension of energy is energy. Momentum also has the dimensions of energy in natural units. So you can see that in natural units, you can write all the units in terms of energy. Okay? So that is the important thing which we have to understand. Now, so this was about natural units.